Hello, this is Homework 4 Part C. So in this section we're going to be dealing with some code. So we can first start it off by typing from scipy.integrate. Integrate. Yes. Import solve underscore IVP. So this is just going to allow us to integrate the right-hand side of our differential equation. So next line of code is going to be import jax.numpy as JNP. We're just doing this as JNP so that when we reference it later, we won't have to type out as much stuff. Alright, next line of code is just going to be importing Jax, library that we will be using. Now we will type from plotly.subplots, import make underscore subplots. It's just going to allow us to import the feature for subplots and then to be able to make the subplots themselves. Next line is going to be import plotly.graph underscore objects as go. And finally, we are going to add plotly. I keep typing plotty. We're going to add these two lines of code which will allow us to make our graphs dark, like black. It just is a little bit more appealing to the eyes, I guess, in my opinion. So last line, templates default equals, and then like I said, plotly underscore dark. We'll hit shift enter just to make sure everything looks good. Waiting a second here. There's my error. Let's try it one more time. Perfect. Awesome. And now we'll move on to the next part. Alright, so now that we have the basics already filled out, we are going to set and start with our initial conditions. So we can first start off by labeling tEnd for the end of the time, and that is going to equal 2,000 seconds. So our next one is going to be SQ2G, and we're going to equal that to jnp.start, and we are going to have it being 2 times acceleration due to gravity, which is 9.81. Alright. Oh, jeez. Okay. Well, little bit of a mishap there. So now we can go ahead and set some more initial conditions. So we have AC1 is equaling to 1, and then we will have AC2 equaling to 1 as well. AC1 being for the first tank and AC2 being for the second one. And then we'll have our area of the pipes that are being used in this situation. So A12 is the one that connects tank 1 to tank 2, and that has area of 0.3. And same thing with our outflow pipe that has 0.03 as well. So now that we have that, we'll go ahead and set our heights. So our initial heights. So the initial height for the first tank is going to be 5 meters, and for the second one, it's going to be 3 meters. So there we go. All right, we'll shift enter just to make sure everything's looking good there. And of course, we have an issue. Don't know why I did start. Square root, or squirt in this instance. All right, there we go. Awesome. All right, so now that our initial conditions have been set, we are going to not import, I guess, but type out our functions or our equations that we derived from parts A and B. So we are going to start off with Q being the flow rate, Q12I, the flow rate between the first and the second tank. It's going, and like I said, this is what we found earlier, A12 times JNP dot sign, and we have to make sure the sign is in here because we don't want that weird negative issue that I talked about in the previous part. So we have our first height being subtracted from our second height, and this is still the initial. So this is going to then be multiplied by our SQ2G, and there it is. Lastly, we are multiplying it by the square root of the absolute value of our heights. So that's JNP dot squirt, and our heights being, or not heights, JNP dot ABS, and then our H1 initial minus our H2 initial. And then double parentheses there. Okay, so now we are going to define our flow rate out. So we have A2 times SQ2G times JNP dot square root of our second height. We don't need to care about the first one anymore because this is for the flow rate out, and it isn't, or flow rate out of the second one, and it doesn't have any relevance in here. So now we'll go to Q1 initial is equaling to Q12I, and then we have Q2 is equaling to Q2I minus Q12I. Lastly, we're just going to add a print statement to make sure, so that we can see our values, make sure everything's looking all good. So we have Q1 initial equaling to, let's find the brackets here, wrong one. It is equal to Q1 any, and then we have Q2 any being equal to Q2 any. All right, and then we'll do a shift enter here, and we have an error. I think I forgot to put the end brackets on that. All right, there we go. We got our Q values. So move on to the next part. So next step of the process is going to be applying the sigmoid function. So we can start it off by adding def, and then we have switch. And in our parentheses, we're just going to put some values that we have been given and that are known. So we have t obviously being for time, v1 for the first velocity, v2 for the velocity of the second tank. And we can go t switch, and finally we'll have scale. This is just to make it so that there are the transformations on the graph. So we can go ahead and end that. And obviously with a function you have to have a return. So we're going to return jax.nn.sigmoid, obviously since this is a sigmoid function, and we're going to do t minus T switch. And that is going to be in parentheses and being divided by our scale. And finally, it is being multiplied by V2 minus V1. And that is going to be then added to V1. So basically, the sigmoid function just takes a number from negative to positive infinity, as well as changing the range from 0 to 1 for the output. So let's go ahead, shift enter. Hey, got that one first try. That's surprising. All right, and we move on. So now that we've created our sigmoid function, we are going to change our flow rates for our desired time. So we can start that off by creating another function, and we'll label this one Q1in with respect to t. And what we will be returning is we're just basically giving values to this part right up here. So we'll return t, stays the same, and our V1 is going to be changed slightly. We are going to make it Q1 ini, which we defined right up here. So like I said, Q1 ini, and then because it is 80% like less efficient, we are going to type in 0.8 times our Q1 ini, and then we are going to set the length of the graph to be 500 seconds, and we are going to set our scale to be 50. We're making the scale 50 just because if we make it 1, it looks really sharp and unrealistic. So go ahead, get out of that. And now we have to do one for the second tank. So we'll do this one Q2 in. T as well, keeping the same thing there. And basically we are returning the same thing, just slightly different due to the fact that it is for the second tank. So we got our T, Q2 ini. Then this one we will do 1.2 times our Q2 ini again. Then we'll set this one to be 700 and keeping the scale 50 to be the same. So we go ahead and shift enter on that. It looks good, but I don't know why. It just doesn't look right from when I was doing it earlier. Oh. Gotta put switch in front. There we go. Okay. Make sure everything's spelled correctly. We'll shift enter again, and it looks good. All right, moving on to the next part. All right, so now we are going to need a function that will give us the right-hand side of our equation, kind of what I mentioned on a little bit before. So first, we're going to import that jax.jit. This just basically compiles the function and makes it run a little bit more efficiently. So we got that. All right. Now our function, since this kind of goes along with the other parts, we have our dh dt, and this is all in terms of time and height. So now we don't really care about the initial conditions anymore. We're moving on from those since we aren't really worried about the steady state anymore, and we just want the rates for the specific height. So h1 we will set equal to h brackets here 0. This one being for the first tank, and then our second height we'll go ahead and just call that 1. Like I said, second tank. Oh, an h there. All right, now we're going to bring back our equations that we typed out earlier. So we have our Q12 equaling to our A12 multiplied by J and P dot sign, making sure that there are no negatives that are going to bother us. Then this is being multiplied by the SQ2G, finally being multiplied by square root of, make sure ABS as well, of H1 minus, not period, H1 minus H2. Alright, now we can go ahead and get our second equation typed out in here. A2 times SQ2G, and then this one, as I mentioned previously, it doesn't really matter, or we don't need to have the second height because it is the final tank, and the first tank has no affiliation with it anymore. Alright, and now we obviously have a return at the end of our function. Make sure that's tabbed in. And we're returning an array here that will be used later on. And for our array, we are going to type out here. So we have our Q1 IN with respect to T, and this is being subtracted from 12. Then it is being divided by AC1. And then our next part is going to be for our second tank, so our Q2N, making sure that the T is there. And that is going to be added to our Q12 minus our Q2, finally being divided by our AC2. Alright, and then we will go, shift enter. And there's an error. Of course there's an error. What did I do? What did I do? Okay. There's a lot of extra hoopla in here. Okay, let's try that. Perfect. Alright, moving on. Okay, so now that we have everything defined, we just need to solve the initial value of the problem. So we can start this off by doing res equals solve. Solve underscore IVP, bringing back what we had earlier. And then we are going to call in our the function we just made, dHdt. And then we're going to do 0, 10. And then we're going to go and add in our heights. So we'll do h1i and h2i. We can close the parentheses there. And then we add method equals redo, and we're just doing this because it will allow us to solve the differential equation. It's not done yet. We do dense underscore output, and that is equal to true in this case. And finally, we'll just do jack equals jax dot Jacobian, and then calling our old function again, dHdt, okay, and 1. So finish off our parentheses, and there we go. Next line we have is going to be tplot. This just allows us to have evenly spaced points on our plot, so it looks good at the end. That's going to be equal to jmp.linspace. This is when I said how we tried to make it look a little good. And, 0, 10, and then 501. Alright, finally the last thing we need to type for this is going to be solution And we're just going to set this equal to res.sol. This will just kind of make it a little bit more compact so we don't have to type out as much later. So we'll shift enter on this. And yes, I do have an error. Wonderful. Oh, here we go. Let's see if changing that works. Shift enter. Perfect. You see, a little error, nothing too big. Alright, I will see you in the last and final part. Alright, so now all we have left to do is just to make the plots. So, we can start that off by fig, and we're just saying fig so we don't have to type all this stuff out that I'm about to type. It'll just make it a little bit easier to use later on. So, subplots, and we'll set the rows equaling to 1, and then we'll do the columns equaling to 2. Alright, so the first fig that we are going to want to look at is going to be for the height of the first tank. So, we can do that by typing out fig.add underscore trace, and then we're doing scatter just because that's the perfect, or the plot that will fit the best with the parameters and stuff that we are using. So the x is going to be tplot, the thing that we made earlier, and the y is going to be sol 0. That's something we defined earlier as well. And then we'll name it so that it looks a little better. H1 representing the height of our first tank. And that about does it. All we need to do is add no, okay, I'm good. I just saw that extra parenthesis and it got me a little worried, but I forget that I have to say row equals 1, and finally the column equals 1. Alright. Yeah, that looks right. So, next fig we are going to make is for the height of the second one, the second tank. So, basically it's going to be the same almost. There's just slight differences for calling back certain functions. So we'll do x equals tplot. The x will be the same for all the graphs. The y is slightly different in this situation because it's for the second tank. So we'll do 1 there. Name obviously is different due to the fact that it is for the second tank. So that'll be h parentheses, not parentheses, quote, h2 end. And then we'll do parenthesis there, and then same as the first one, can't forget the comma, row equals 1, column equals 1. So now the next figures that we are going to add is for the flow rates of the tank. So we'll start off with the first one. So we got that here, and then x equals tplot, same as all the other ones. But our y is slightly different now because we're talking about the flow rates, not the heights, whereas we changed the heights earlier to the sol, like SOL. This one slightly little different. So we'll do Q1in, and then we'll do tplot in parentheses, and those parentheses, naming it, we name it Q1in just to go along with the flow rate that we are looking for. And same as the other ones, row equals 1, and column for this one we are slightly changing it, it equals 2. So finally we have our last one, this one being the flow rate for the second tank. So Very similar. Not much changing here. Just so for right now, so t-plot, obviously, stick along with the other ones. The y for this is going to be equal to q1n, q2n. We are on the second tank now. T-plot, naming this one q2n, and then finally row equaling 1 and column equaling 2. And then add our last end parenthesis, shift enter. Everything's looking right, and there we go. There are our graphs. Alright, thank you very much for watching, and I will see you next time in the exam.